So now we're gonna talk about the activation energy of the water, right? We have already explained that. So by the way, always know that when we talk about the activation energy, we are talking, I said, it is actually from the activated complex to this thing over here, to the reactants. Don't pass and go to the products. Be careful. It's the activation energy, right? The minimum energy that is needed for the reactants, for the reaction to take place, by the way. So without this energy, the reaction won't take place. Meaning we cannot just jump there to the products, or we cannot just jump like this. We need the energy. We need that energy. You get it? So that's the reason why we need the activation, activation energy. So here I want to talk about the but here I want to talk about a new activation energy. Look, C. Now we're going to talk about C. Look this, the purple color. Now, remember, from this reactant to that product, it's a chemical reaction, right? It's a chemical reaction. So when we have the chemical reaction, let me make an example of this so that we can understand. Here is, let me take label. Here is label. And then here is, okay, let me say there is a boy called Lebu. There is a girl called Rachel, right? And these two guys, they want to date, right? Meaning, we have Lebu and Rachel. They want to date, but they're afraid to date each other, right? They have crush on each other. Lebu and Rachel want to date and form a couple, but they cannot. They can, it's just that they're afraid of each other. So let's say first year at university, Lebu sees Rachel, they are not dating. They just eyeing on each other, giving each other eyes. Second year, they are not dating. Third year, they start dating. You see, that reaction of Lebu plus Rachel to form a couple, it took time. It took 3 years for that reaction to take place. But now, because I know Lebu, I know Rachel, and I'm a friend to them, I go to Lebu and I say, Lebu, and when I see you're looking at Rachel, it's first year, right? I say, Lebu, you're looking at Rachel. And then I go to Rachel, Rachel, you're looking at Lebu. What's happening? Yeah, ish, kwababa, 1, 2, 3, he. And then me as Tepo, what I'm gonna do is, again, we are in first year. Me as Tepo, what I'm gonna do is, I'm gonna tell Lebu about Rachel. And I'm gonna tell Rachel about Lebu. What will that do? Will stimulate the relationship, right? Will make you guys to date within short period of time. So this is Tshepo, the middleman. So Tshepo, he acts as what we call the catalyst. So catalyst, what it does is it speed up a reaction without being part of that reaction. So meaning I'm going to speed up the process of Lebu and Rachel together to form a couple. I'm not going to be the part of their relationship. I was just there to speed up things or to spice things up so that Rachel feels good about Lebu and Lebu feels good about Rachel. And therefore, the reaction will then take place to form what you call the product is going to be a couple. You understand? But when Lebu and Rachel never had a catalyst, they were just there hanging. They dated after some years, man. The reaction happened, but it took time. But because of a catalyst, it happened in 1 year, which is me, Tab. So when you talk about the catalyst in chemistry, guys, with catalyst, okay, amount of energy needed to start the reaction if a catalyst is added. Look, the energy is super high, we need high energy for this reaction to take place. But in this chemical reaction, when we add a catalyst is not going to be the part of the reaction. It is just there to make reaction to be faster. It increases the rate of reaction. Reaction happens fast. So meaning it is going to lower the activation energy. You see, now we have new activation energy, which is let me erase this a little bit. Now you see we're going to have a new activation energy, which is this color over here, the blue one. You see, we have a new graph now. We're no longer focusing on the red graph. We're focusing on here and this one. The activated complex has been lowered. It has been lowered so that we don't need more energy. If we need more energy, we need more time. If the activated complex is lowered, therefore we need at least we lower that more energy is needed. So for reaction to reach this energy, it won't take time. So the reaction will happen fast. You understand? So this is new activation. The C part, C, it is new activation energy. And the red one, the blue one, B, the blue arrow indicates the activation energy, the old one. Without catalyst, by the way, you can say the blue arrow, it is activation energy without a catalyst. But the purple arrow, it is the activation energy with a catalyst. So what does the catalyst do? Catalyst lowers activation energy by dropping the activated complex. You understand? So catalyst, it lowers. Look at this activation energy is very high. And this one is low, it's less. You see, it's at this point over here with this activated complex along with it. And therefore, the reaction will happen faster. When C is added, when catalyst is added, the reaction will take place faster. Let me give you an example of let me give you a good example where catalyst works. When you wash your clothes, do you know that you can wash your clothes without a soap, right? If your cloth, it has a stain, maybe a bit root or I don't know, it has a stain, and you're washing it with water. You're washing it with water, washing it with water. That stain, it will get removed, but you need more energy, guys. For you to do that, to get rid of that stain without soap, you need more energy. But when you add soap, maybe your washing powder soap, then you start washing that cloth, what's going to happen? The stain will get removed very, very fast. Why? Because you added the catalyst, which is the washing powder. You know why chemical engineers design those things? If you're a chemical engineer, you're gonna work at those industries where they form the soaps and stuff. It's because this is why you're learning this topic. It's because catalyst, but again, washing powder, it is the catalyst, if you didn't know that. You've learned this in grade 10, if you remember, in life sciences. In life sciences, you have learned that the catalyst and all of those things, they speed up the reactions. Remember that? And then types of catalyst, we can talk about the soap, right? It's the enzyme, by the way. Catalyst, it's the same as enzyme. Okay, it's the same as enzyme. So that means lock and key model. Remember that lock and key model whereby the soap will be able to unlock that stains, and then those things form a substrate, that's the same idea. That's the exact same thing. This is where physics meet biology. You understand? So that's what catalyst does, by the way, in reality. So yeah. Okay, so that's what we mean when we talk about the activation energy with catalyst. So what is the catalyst? Speed the reaction rate by lowering the activation energy to start the reaction gives alternative pathway. It gives the alternative pathway. This pathway is very long. So we want the alternative pathway, the short routing and a shortcut, so that we get to the products fast. That's why we have the chemical engineers. The chemical engineers is their work to do these things. They want the ways to form the product very, very fast. I mean, like we have high demand of society, right? People are demanding things. Things are being used. So the more population increases, the more products we need. So we introduce things like catalyst while we have the chemical reactions so that we can form our products quickly in chemical industries. See, so now you're learning this topic with real world application. Why do we need this topic? Now here, let's talk about the exothermic and endothermic reaction. In a chemical reaction, there is usually a temperature change, right? It's either temperature increases or decreases, but there is a temperature change in a chemical reaction. You need to know that. So in an exothermic reaction, the temperature goes up. That's how temperature changes, meaning it starts from low and then it goes up. Your reactant starts from low, with low energy, with low temperature. Now we're talking about the temperature. Starts with low temperature as the reaction takes place, and therefore the temperature goes up. Why? Because heat energy is given out. Obviously, it's hot now. Like when you touch the wherever the vessel at which the chemical reaction will be taking place, when you touch the walls of the vessels, they will feel high. They will feel hot, right? When you touch it with your hands. Therefore, in an endothermic reaction, the temperature goes down. You should know that. Why? Because heat is taken in. We are not releasing heat. We are taking heat. So the temperature goes down. It feels like it doesn't make sense, because in endothermic reaction, we are taking heat energy in. So how does the temperature go down? It sounds like it doesn't make sense, but it does. Okay, it does make sense because we are talking about the whole completed reaction. So here the temperature really goes down. Why the temperature goes down? Because the products are consuming heat energy, all of it. They are sucking that energy to themselves. They're not giving the energy out. So that's why when you take your thermometer in that chemical vessel, and then maybe you want to read the temperature inside of that vessel, the thermometer will indicate to you the temperature is down. Why the temperature is down? Because those reactants, they suck the energy in. They use the energy in. So there's no energy to the surroundings. So that's why the temperature drops. You understand? So that's endothermic reaction, where we have the lower temperatures. That's why the reaction is cold. When you touch the walls of the container, you feel like there is no heat that is being given off. It feels like it's cold. I can touch it with my bare hands. So that means we're talking about endothermic reaction. So now here we're going to look at the examples of the exothermic reaction. Yeah. Exothermic reaction. You will learn combustion in more detail in grade 12. So now combustion is a common example of exothermic reaction. You know what is combustion? Guys, maybe some of you in future, you want to work in petroleum, for an example, Bososol or so at Sosol. I'm just going to pick Sosol, Sosol company. Maybe let's say you want to work there as a chemical engineer, as a chemist. There, they are forming what? They are forming there is this thing that we call the cracking of organic compounds. Methane is an organic compound, by the way. So, but this is a short chain. So this is what we call the combustion reaction. Combustion reaction is when an organic compound react with oxygen. Okay. So what is this organic compound? You see the petrol that the car uses. You see the gas that you use at home for the gas stoves, uh, those gases, body butane, methane, all of those things. Those are the organic compounds. The fossil fuels, such as body coal, those are the organic compounds. So when organic compound, there is a presence of oxygen. Have you realized that, guys, when you want to start a fire, you'll start to blow at the fire. You'll be like, or you'll use your cardboard, try to do what? Try to, but again, you're actually blowing oxygen onto that process so that that oxygen can react with organic compound. It could be methane, propane, butane, does not matter as long as it's an organic compound. So that organic compound, we can start to have heat energy, therefore we receiving the fire. I get the reaction is hot. That's why it's exothermic. The reaction now it becomes hot, right? There is water at some point, smaller than water, and there is a carbon dioxide, which is that smoke that we see out of the fire. Basically, this type of reaction is called the combustion reaction, when organic compound, in this case, we're using the methane and oxygen. Oh, here's coal. And then for carbon, we can use coal with oxygen. We form carbon dioxide and heat energy. So this is one of the examples of the exothermic reaction where we give energy, heat energy out, or enthalpy out to the surroundings. And then another example, we have neutralization. Is another example of exothermic reaction. When you neutralize, it's when you combine acid and a base. We're going to do acid and base, by the way, here in grade 11 and in grade 12. I love that topic. So when acid combine alkali is a base, by the way, okay? It's a base, alkali. So when acid combine with an alkali, we're going to have salt, water, and heat energy. For the fact that we have an heat energy, therefore we are talking about the exothermic reaction. So some type of acid and base reactions, we get heat energy. Always salt. Salt will always be formed. You will see when you do acid and base topic. So acid and base, when they combine together, salt will always be formed. Some they form carbon dioxide, some they form water, and then heat. If heat energy is released, therefore we are talking about the exothermic reaction. The reaction is going to feel hot. When you take your acid inside of a beaker, you combine it with a base, you will start to feel the test tube being hot. It's because of the reaction. It is exothermic. The symbol, I told you this, right? The symbol to show change in amount of heat energy is called delta H, pronounced delta H. I told you, right? Which is enthalpy. Don't forget that is delta H. I showed you that this it represents is the same as delta H. Now, here's another thing that you need to learn or to understand. We are still on the very same graph, right? Is this endothermic or exothermic? It's exothermic. It's exiting at the bottom. It's exiting at the bottom. Exit, exothermic. Right, sharp, fine. So we have the reactants there. We can see that we have the product. We have already spoke about this, that from this to the activated complex, we are actually talking about the what? Activation energy, right? So we are good with that one. Now we have just introduced a new thing here, which is called delta H, which is the heat of the reaction. Now, look, remember, here we are talking about the potential energy of the products. Here we are talking about the potential energy of the reactants. Of the products, and then here for the reactants. So when you want to determine the enthalpy, which is the change of heat of the reaction, you're going to say potential energy of the product, which is this value over there, subtract potential energy of the reactants, which is this one over there. So my question is, when you look at the difference between P and R, between the products and the reactants, so remember, the energy of the product, it is low. So let's say maybe it's 1, for an example. And then the energy of the reactant is higher than the energy of the product. Let's say maybe here, for an example, it's 2. So you're going to determine delta H by saying 1 subtract 2. You're going to get negative number, which is going to give us negative 1. I don't care about the number. I'm curious about this negative sign. So here we can see that delta H is going to be negative. We can see that here, delta H, it is negative. How did I prove that delta H is negative? Obvious. The energy, each and every time, this is the formula that we use, by the way. So you can say delta H is equals to H of the product subtract H of the reactant. If you don't use P, E, or E like this, you can use this notation. You can say H of the product subtract H of the reactant. That's why delta H, it is between the reactant and the product, which is here. So to determine delta H, we use HP for the product minus HR for the reactant. So I'm saying to you, according to this graph, according to the shape of this graph, we know this is exothermic, right? So how do we know this is exothermic? We gave the reasons to see why do we say this is exothermic reaction. Another way to see that the reaction, it is exothermic, it is when delta H, it is negative. So how are we going to prove using this that delta H is negative? We can just assume by just using this. We can say, obvious, this here is the energy of the product, and this, maybe let's assume it's 1, or you can assume 2 or whatever, any number. But when you assume the number, the energy for the reactant is supposed to be above. Obviously, it's above this one. It's supposed to be the greater number than this. Let's assume that therefore it will be 2. So using our equation to determine delta H, let's say enthalpy for the product, it's 1. We say 1. Enthalpy for the reactant, it's 2 there. It's 2. So what is 1 minus 2? We get -1, right? So we get the negative answer. For the fact that we get the negative answer, it shows that we are talking about the exothermic reaction. That's why here we say for an exothermic reaction, delta H is negative. This means that the heat has been lost from the reaction. Yes, heat has been lost from the reaction because we have learned that exothermic reaction, it is a reaction where we lose heat. So now we just spoke about the examples of exothermic. Now let's talk about the endothermic, and then I'll close it after this. Now, endothermic reaction tend to be less common, right? Like I said, most of the times we don't know, it's less to find the reactions that are endothermic. It's not popular, right? Where we release, when the chemical reaction takes place and then we release heat, it's less common. Unlike exothermic, there are main examples of exo, right? But it's fine. Nonetheless, let's do this with what we have or what we know. So when you take ammonium nitrate, right, crystals in water, just know that you are performing an endothermic reaction. So, meaning according to the chemical reaction, you can look at it like this. So ammonium nitrate plus water combined together, we're gonna form our product, which is ammonium nitrate solution, and negative energy. You see, this is not positive energy, it's negative energy. So that means if we take this negative energy, we take it to the other side of the equation, it's going to be positive heat energy. Okay, so according to this reaction, we have to understand that the temperature of the reactants, it's 20 degrees. That's how we saw that the energy was added on this side, because looking at the reactants, we have high temperature, but looking at the products, we have low temperatures, right? And we know that when you have low temperatures of the product, it means that there was no energy lost. But for a fact that we have high temperature on the product side, on the reactant side, it means that we have more heat, we have more energy this side, we have more heat energy this side compared to that. So this temperatures also gives an insight of how to read whether the reaction it is endothermic or exothermic. So in future, guys, I can be this person if I was an examiner. I can say, look, I can say I have the reaction A plus B is equals to C. And I say the temperature for A plus B, it's 361 Kelvin. And then the temperature for C, it is 258 Kelvin. And then I ask you, is this reaction exothermic or endothermic? Lebu, how are you going to answer this question? Is this reaction exothermic or endothermic reaction?
Endothermic.
You say it's going to be endothermic reaction. So my question is...
No, sorry.
Oh, okay.
Exothermic.
Endo.
Exo.
Exo. Okay, why do you say it's exothermic?
Because the reactants have more energy. Oh, we're talking about temperature. Sorry.
Yeah, it's temperature, yes.
I'm not sure.
That means you're not listening to me when I was explaining this. Okay, I'm saying here we're
Endothermic.
explaining endothermic reaction, right? So ammonium nitrate, when you dissolve your ammonium nitrate in water, you're gonna form this product. And you see we have negative heat energy. So I'm saying to you, we know that here we're talking about endo. So it's negative because it is on this side. But it was gonna be positive, this heat energy mathematics. If I take heat energy, this side is gonna be positive heat energy to show that I am taking in heat energy on the reactant side. So I'm saying, how did they realize that this reaction it was endothermic? It's because the temperature of reactants is which is the temperature. I'm not talking about the enthalpy or the energy in kilojoules. It's Kelvin. It's temperature. Units for temperature, by the way. These are the units for temperature. It's Kelvin, or you can use degrees Celsius. Ne? So the temperature of the reactants here is 20 degrees Celsius. Of the reactants, it's 20. And then of the products, it's 13 degrees. So for the fact that here we have high temperature on the reactant side, that means there was high energy take in this side of the reaction. But because here we have low temperature, that means we didn't release from 20 to 13. Did we release energy? No, we consumed the energy because the temperature of the product, it is less. It's just 13 degrees Celsius. That's another way to look at whether the reaction is endothermic or exothermic. So here I said, let's say we have an example. We have reaction A plus B to form C. So they say the temperature of AB is 361 Kelvin. These are the units for temperature. We use Kelvin, or we use degrees Celsius, or we use Fahrenheit, or we use the Rankine. Okay, those are the units for temperature. So the temperature of A plus B of the reactant is 361 Kelvin. And the temperature of the product, which is in this case, is 258 Kelvin. So my question is this reaction exothermic or endothermic?
Endothermic.
Why do you say it's endothermic?
Because the temperature of the reactant is higher.
Exactly. You see, there was a consumption of energy on this side because of high temperature. So this side, because, yeah, that's it. Good. So now here we have, let's have a look at this one, endothermic. Why for endothermic reaction, delta H is positive? Look at this graph. Look at the reactants. Look at the products. Now this graph, it doesn't exit at the bottom. So if it doesn't exit at the bottom, therefore it's endothermic. One thing for sure that I know, it ends at the top. It doesn't exit at the bottom. But by the way, the reactants are lower, the energy of the products are high. So we know, remember, activation complex will always form the reactants. Don't take it because now the product is here. So you're going to say it's from the activation energy will always start from the reactants to the complex, to the activated complex all the times. So we still have potential energy on this side. We have the cost of reaction or the progress of reaction on this side. So we have delta H. Delta H, it is enthalpy, which is the heat of the reaction. In this case, to determine delta H, we can say H of the products subtract H of the reactants, just like how we did it on the previous one. So look at this. The energy of the reactant is low. The energy of the product is high. So obvious, if this is low, let's say more, it's 2, therefore I'm going to have to take the number that is above 2 because you see it's above 2. So let's say here it's 4, for an example. So when I want to determine delta H, I'm going to use this portion over here. I'm going to use H of the product, or energy or potential energy of the product. So the potential energy of the product, let's say it's 4. The potential energy of the reactants, let's say it's 2. So 4 minus 2 is a positive number. I don't care about the number. I get positive 2. So for a fact that I get positive, I get my delta H to be positive. That's why we say for endothermic reaction, delta H is positive, meaning this graph represents endothermic reaction. You can look it in many ways. Look at delta H. If they give you reaction, look where the heat is placed. Is it placed on the right-hand side or on the product side? Look at the shape of the graph, right? Look at the energy of the products and the reactants. That's the way to tell whether we are talking about the endothermic or exothermic. Collectively, you can look at those things. Okay, so yeah, let's just recap before we end the session then. What have we learned? We have learned exothermic reaction, heat is given out, right? Let's recap again. We have learned that delta H is negative for exothermic reaction. And therefore, using this, we saw that the energy of the reactants is higher than the energy of the products. Now let's go talk about endothermic. We know that for endothermic, heat is taken in. And the delta H is positive for endothermic reaction. And then again, by looking at this graph, we can see that if you have the increasing energy this side and then time, the course or the progress of the reaction, the energy of the reactant is lesser than the energy of the products. And then we also learned that another word for heat energy content of a compound is enthalpy. I told that the enthalpy, it is the heat energy of the reaction. We can just say it's a heat of reaction. And then the other thing that you need to know is that you need to know that the unit for energy is in joules. Okay. For example, we're talking about delta H. We can talk about 356 joules. Sometimes we can say delta H is 36 kilojoules. So kilo means 1,000, joules means just joules. So the units for energy, whether enthalpy is energy as well, but the units for energy we use joules. Right? And then 1,000 joule is the same as 1 kilojoule, like I told you that kilo means 1,000. Okay, so meaning 1 kilojoule is the same as 1,000 joules. You see, 1 kilo means 1,000. I agree here we have joule, but 1 kilo means 1,000. So 1 kilojoule is the same as 1,000 joule conversion. And then making and breaking bonds. Why are the energy change in chemical reactions? Because chemical reaction involve the making and the breaking of the bonds. That's what we spoke about at the beginning. So making of the bonds, having a look at this, this is methane. We're gonna have to break these bonds, right? We're gonna have to separate these bonds together. And then when breaking a chemical bond, energy is put in. We saw that, right? We spoke about it. And therefore, if energy is put in, then this must be endothermic. And then when making a chemical bond, energy is given out. If energy is given out, then this must be exothermic. And then breaking bonds is endothermic, making bonds is exothermic. So remember, so what happens in an endothermic reaction? We have the reactants, we have the products. Here we're taking energy in, it's endothermic. Here we're taking energy out, it is exothermic. So more energy has to be put in to break the old bonds than is released when the new bonds are formed. So what happens in exothermic reaction? We're taking energy in and then energy out, but more energy is out. Remember, it's exothermic. More energy is out when new bonds are formed than is taken in when the old bonds are broken down. That's exothermic. So we can show the energy changes in the form of energy level diagrams like this, like for example, methane and oxygen reacting together, activated complex where we have the intermediate and therefore we form our products over there. I've already explained this. we can look at this as the energy. From there to there, we have 2,704 kilojoules per mole. And then from this point to there at the bottom, we have 3,462 kilojoules per mole. And therefore, this negative 720 kilojoules per mole, it is enthalpy. It's enthalpy, which is change of the um, uh, change enthalpy, right? Change of energy, right? Change in energy of the products and the reactants. And then we have energy. Here are the units, progress of the reaction. It's the same as those graphs that I showed you here, but here with things. And then now we come to the end of the lesson. In this lesson, we have covered what? Exo and endothermic reaction, making and breaking bonds. And thank you for this lesson.